Hello students, very good afternoon to you, all of you. So today I will cover the part 2 of the engineering services PYQ for the preliminary exams. Part 1 I have covered in my earlier lectures. So today it is part 2. So let's start. A beam EI is constant of span L is subjected to a clockwise moment at both the ends A and B. So the direction of the both the moment is same. The rotation at A works out to be how much? There are 4 options. So moment are in the same direction. This is M and this is M. So it is like this. This is L, this M. So as per principle of superposition, I can treat it like this. Effect of the moment I can treat separately. This is M plus effect of this moment I can treat separately. So because of this moment, it will rotate like this. So this is a rotation A, B, and because of this, it will rotate like this. So this is theta. This is theta B1. This is theta B2. This is theta A2. So my net deflection theta A will be equal to this minus this, this minus this. So because of this, this will be, as we know, this will be ml upon 3I. So this theta A is equal to ml upon 3I. As we know, when the other end is simply supported, if you apply a moment m, then slope because of this will be ml upon 3I, and the half of this will be half of this. So this theta B, this will be ml upon 6ei. Similarly, if this is m, then this slope, this theta will be ml upon 3I, and half of this will come here. This will be ml upon 6ei. So now my this minus this angle theta A1 minus theta A2, this will give the net rotation at this point. This minus this, the direction of the both are different. So this is ml upon 3I. So this minus this, so it will be ml upon 3I minus ml upon 6I. So ml upon 6I I can take common, so it will be 2 minus 1 means 1. So it will be ml upon 6ei. So the answer will be this one. A probe cantilever of span 4 meter is fixed at A. The beam carries a UDL of 1 ton per meter over the entire span. The reaction at B will be, this is like this. This is the case. This is a probe. So as we know, the net deflection at this point is 0. So whatever deflection because of this UDL, it will deflect like this. So this is delta, and because of this probe, it will deflect like this. So this, if this is theta 1, this is theta 2. So this theta 1 is equal to theta 2. So that the net deflection at this point is 0. So this deflection theta 1 is equal to, the formula is W L4 upon 8EI. This is the formula, and because of this point load, it will be R L cube upon 3 EI. This is the formula. Now this EI and EI will cancel, and this L cube, so it will be WL upon 8 R by 3. So these 3 I can take. So it will be R is equal to WL upon 8. W is 1 ton per meter and length is 4 meter. So it will be 3 by 2 means 1.5 ton. For determining the deflection y of a loaded beam at a distance x by Macaulay's method, which one or more of the following are used? Suppose I have a beam like this, and by Macaulay method we can find the slope and deflection at any point. So the basic differential equation is this one, where E is the flexure rigidity of the EI, M is the bending moment. Successive integration, yes, it's basically a double integration method. Known position of zero deflection means deflection at this point is 0, it is 0 here. So all this we take into account in my Macaulay's method. So select the correct answer using the code given below. So all are correct. It means the option, this one is right. Moment of the same sense are applied to both the ends of a simply supported beam. The ratio of the rotation of the two ends is 2. What is the ratio of the applied moment? So this is simply supported beam, and there is a moment, this is A, this one is B. If say this is M2 and this is M1, the direction of the both are same, L is the length. So it will deflect like this. So this will be theta A, this is theta B. What he says, that the ratio of the rotation of the two ends is 2, means theta A upon theta B is equal to 2. What is the ratio of the applied moment? Means this M1 upon M2, this is 2, M1 upon M2 ratio is to be known. For this, as I know in the previous questions, as I had discussed, my slope at this point I can treat it separately. It will be like this. This is M1 and this is M2. So it will deflect like this and it will deflect like this. This will be, suppose this is theta A1, this is theta A2. Similarly, if this is theta B1, this is theta B1, this is theta B2. Now my theta A, this net theta A will be this minus this. Theta A is equal to theta A1 minus theta A2. Similarly, this theta B will be theta B1. This will be theta B2 because of this and this, minus theta B1. So this minus this. So this will obviously be more, this will be less. Now, as I know, this theta A1 will be, because of the M, it will be ML upon 3I. Formula is this one, M1 L upon 3I, and because of this it will be M2 L upon 3I here, and it will be M2 L upon half of this will become here. Similarly, it is ml upon 3i, so it will be m1 L upon 6ci. So my net rotation at this point will be this minus this. This will be this minus this. It means m1 L upon 3i minus this m2 L upon 6ci. This will be the net theta A divided by theta B. Theta B will be this minus this. This is more. So this will be m2L upon 3i minus this is m1L upon 6ci. This will be theta A, and theta A upon theta B is equal to 2. So L upon EI, this L upon EI, L upon 6EI you can take common. So it will be 2m1 minus m2. Similarly, L upon 6i you can take common. It will be 2m2 minus m1 is equal to, this ratio is 2. So it will be 2m1 minus m2 is equal to 2 times of this will be 4m2 minus 2m1. So this will become, if I take this towards left side, it will be 4m1 is equal to 5m2, means m1 upon m2 is equal to 5 by 4. So this will be the answer. The free end of a cantilever beam is simply supported. So there is a roller. Free end of a cantilever beam is supported at the free end of another cantilever beam. So there is a roller, using a roller as shown in the figure. What is the deflection at the roller support? Deflection at the roller support. So this is basically like this. Now if I draw the free body diagram, it will be like this. This is P 3A. So this roller will provide a reaction here, and for this beam it will be like this. So my net deflection at this point will be equal to deflection because of this. My net deflection will be, this will be this minus this. So net effect will be, this load will try to deflect it toward downwards, and this will be towards upward. So this minus this, it will be this minus this. So it will be P minus R into 3A cube upon 3EI. So this will be the net deflection, and this will be equal to this one, or you can say deflection because of, you can treat it like this. This is P and this is R. So this minus this, since there will be some deflection due to roller, so this deflection will be P into 3A cube upon 3I minus, due to this reaction it will be R into 3A cube upon 3I. And this net deflection, whatever will be the net deflection will be the same. So this downward minus upward, whatever will be the net deflection at this point, that same deflection will be at this point. So it will be R, and this is 2A cube upon 3I. So this 3I and 3I will go, and this will be A cube, and A cube will also go. So this will be 27P minus 27R, this will be 8R. So 27P is equal to 35R. So R will be 27 upon 35. This is the value of the R, and my net deflection is this net deflection is equal to this net deflection. So this will be R into, this is R into 2A cube upon 3I, and this R is equal to how much? This is P. This R is equal to 27 upon 35. This P. This will be 8 cube upon 3I. So this will become 72P A cube upon 35 EI. 72P A cube upon 35 EI. So no answer is matching. So there is some problem in this options. The correct answer is this one. So this is the correct answer. 72P A cube upon 35 EI. 72P A cube upon 35 EI. This is the correct answer. Some problem is there in the question. What is the vertical displacement at the point C of the structure shown in the figure? So vertical deflation at this C point, I can find it by strain energy method. Suppose if I applied a imaginary load Q, then it will be, so as we know, as per Castiglione theorem, delta partial derivative of the strain energy stored with respect to this Q will give the deflection at this point. So after differentiating and integrating, I will put the value of the Q is equal to 0. So this is basically m square dx upon 2I is the strain energy formula, and partial derivative of this. So this will be, suppose this, so this will be m into delta m upon delta q into ds upon ei. So it will be m into delta m upon delta q into ds upon ei. So this will give the deflection at this point q, and I will put the value of the q is equal to 0. So if I take for this portion, so delta u upon delta q is equal to, for this portion, what is the value of the m? This will be p into y, and partial derivative of this with respect to q, this will be 0 into ds upon ei and 0 to a, plus this will be, so parts m at this point will be, this will be, this is sagging p into a, and this will be hogging. So this will be minus q into x. So this will be m, and partial derivative of this with respect to q, this will be minus x into dx upon ei, and integration from 0 to 3a. So this one will become 0. So, and this will be, in this I will put the value of the q is equal to 0. So this will become 0 into 3a. So pa, this will be 0. I will put the value of the q is equal to 0 since this is imaginary load. So this will be pa into minus x into dx upon ei. So this will be minus pa upon ei, I can take common, into x into dx 0 to 3a. This will be pa upon ei into x square by 2 means 3a square by 2, and this will be 9 pa cube upon 2 ei, means this one is the right option. The deflection at the free end of a uniformly, so this is a cantilever and length is 1 meter, and the deflection at this point is 7.5 mm. What is the slope at the free end? So slope I have to find. Now this deflection is equal to, formula of deflection is, what is the formula? If suppose this is w, so it will be w L4 upon 8 ei. This is the formula for deflection, and the deflection is 7.5 mm. So, and formula for the slope at this point is WL cube upon 3 ei. So this I have to know. Suppose if I divide this by this, so it will be L here, so it will be L upon 8 into 3 upon 1, and this will be 7.5 upon this one. This will be 8 into 7.5 upon 3. It's the UDL. What's the UDL? So in case of UDL, the slope is 6. So it is 6 ei. Basically, it is 6 ei. So this will be 6. So 8 into 7.5 divided by 6 into L. So and L is equal to 1 meter. So this will be 8 upon 6. So it will be 4 upon 9 into 7.5 divided by L. L is equal to 1 meter, means 1000. So this will be oh, this will be 6 upon 8, means 3 by 4. So 3L by 4 is equal to this one, and this is equal to 7.5 into 4 upon 3L. So it will be 75 upon 4 upon 30 into L is equal to 1 meter. 1 meter means 1000 mm. So this will be 300. So it will be 10. 10 means, so 1 upon 100. 1 upon 100 is equal to 0.01. So this is the answer. If in the propped cantilever shown in the figure given below, what are the value of the bending moment and shear force at the spot? So bending moment and the shear force at this point I have to know. For this, first of all, I have to know the reaction here. Reaction at this point. So this will be, as we know, we can treat it separately like this, and there will be a prop reaction like this one. This is R. So as this is propped, so net deflection at this point is 0. So this will deflect like this, and because of this it will deflect like this. So my net deflection due to this load, this deflection is equal to this one. And what is the value of the deflection at this point? The load is applied at this. So deflection at this point, as per Maxwell reciprocal theorem, if I have to find the deflection at this point, load is acting at this. So this will be equal to, this is P. So deflection, because at this point, because of this load P which is applied at this point, so deflection at this point because of this load is equal to deflection at this point because of the load applied at this. Means if I applied my load at this point, then whatever will be the deflection at this free end, the same will be equal to this one. If I applied at this load is applied at this point, so because of the application of load at this point, suppose this is C and this is D. So this deflection delta C because of the load at this D is equal to the deflection at D because of the load applied at C. This is Maxwell reciprocal theorem. So if I want to know the deflection at this point, then I will apply the load at this point and I will find the deflection at this point. And as we know, this deflection will be deflection at this point. So this is P. So P into this distance is 3a. So RL cube upon 3I, this is the formula. This deflection plus slope at this point, P into 3a square upon 2I, this is the slope, into this length. This length is 2a. So this deflection is equal to this deflection, and this is equal to deflection because of this prop will be r into this distance upon 3I. So EI, this will go, and this will be a cube also will not be present. So this will be 27 divided by 3. So it will be 9p plus this is also 9p, and this is equal to, this is also 9r. So this will be p plus p is equal to r, means 2p is equal to r, means reaction at this point, this reaction is 2p. So this reaction is 2p for sigma v is equal to 0. This is 2p upward, this is p. So it means reaction at this point will be also be downward, will be equal to p. And if I want to know the moment at this, so taking moment at A, so MA will be, this is hogging P into total is 5PA. So P into 5A, this will be sagging minus 2P. If I say this is hogging, I can take minus, and this will be positive. So 2P into 3A is sagging. This will be minus 5, and this will be plus 6 into PA. So this will be 1 PA. So bending moment will be PA, and shear force will be equal to the reaction at this point. If you draw the shear force diagram for this, it will be like this: P, then P, and there's P like this. So this P is the shear force at this point. So this one is the right option. There are two lists: list 1, list 2 loading condition, and list 2 denotes the maximum slope. And select the correct answer using the code given below. A list E is Young modulus of elasticity, A is the moment of inertia, I is the moment of inertia of the cantilever with concentrated load W at the free end. So slope, maximum slope in case of cantilever with concentrated load at the free end. So slope here will be WL square upon 2EI. So the maximum slope, and in this case cantilever with UDL, so it will be WL cube upon 6EI because of UDL. Simply supported beam with concentrated load at the center, it will be WL cube upon 48 EI. And simply supported with UDL, oh, this, I think this is wrong. We are talking about slope. So slope will be slope of the simply supported carrying UDL. This will be WL square upon 16 EI. Case of simply supported carrying UD, so this theta is WL square upon 16 EI. In case of UDL, it is WL cube upon 6 EI, and simply supported beam with UDL, this is WL cube upon 24 EI. So this D will be this one, WL square upon, this is WL square upon 24 EI. So D will be with 2, means this and this. So D will be 2. Then C is equal to WL square upon 16 EI, means this one. So C with 1. So it means this is the right options, and B with B 6 EI. 6 EI means B with 4, and A, this is 2 EI. So A with 3. It means this one is the right option. This is a load case and expression for slope and deflection, and select the correct answer using the codes given below. Slope for the tip load of W. So these all the formulas are for cantilever. So you can say, so due to slope for the tip load, means load at this, so slope, this will be WL square upon 2 EI, means this A with 4. Deflection for the tip load of W, deflection will be WL cube upon 3 EI, B with 3. Slope for total UDL. So in case of UDL, if I say there is UDL and the total UDL is W, means this intensity is W upon L. So in this case, slope will be W L square L cube upon 6 EI. This is the formula, and this W is W upon L into L cube upon 6 EI. So this will become WL square upon 6 EI. I think some mistake is there. So this will go with this. And deflection for the total UDL. Deflection will be, as we know, WL 4 upon 8 EI, and this will be W upon L into L4 upon 8 EI. It will be WL cube upon 8 EI. So D with 1. So A with 4, B with 3. A4, B3, and C2 and D1. C2 and D1, means this is the right option. In the structure shown in the figure, what is the distance through which the points A and these points A move towards each other. So deflection, it will deflect, suppose like this, and so total deflection will be this plus this, and both will be same. So whatever will be the deflection at this point, then same deflection will be here. So this plus this, the deflection at this point will be equal to how much? For this I will use the strain energy method. Strain energy method, the load is applied. So as we know, U is equal to m square ds upon 2I is the formula, and for this portion it will be, if I say this is y, so it will be py, this is the moment at this points, into square into dy upon 2I. I will integrate it from 0 to 2a, and the same for this, so I will multiply it by this by 2, and for this portion it will be, if I consider this x from here, so bending moment at this point will be how much? This will be p into a, p into 2a, and this will remain constant, p into 2a into dx upon ei. I will integrate from 0 to a, and this will be p square into y square. Ei I can take common, 1 upon ei, if I take common, so it will be p square into y square dy, so it will be y cube upon 3 plus this will be 2pa into y, it will be so this will be 1 upon ei into p square into 8 cube upon 3 plus is p into 2a. Oh, p into 2a, this is m, and square of this. So this will be p square into 8 cube upon 3, and this will be this will become this will be 4 p square a square 4 p square a square into a. So this will be 4 pa cube. If I take p square a cube upon 3 ei, so this will be 8 plus this will be 12. So this will be 20 so 20 upon 3 P square A cube upon 3 EI. So this will be the total strain energy stored. U is equal to P square A cube upon 3 EI into 20, and deflection at this point will be equal to partial derivative of this with respect to P. So this will be 2P A cube upon 3 EI into this 20. So this will be, I think some problem is there, 8 upon 3. So yes. Oh, this will be okay. And for this plus this will be 2 times of this, plus for this portion, if I take, this will be P into 2A, P into 2A. This is M square dx upon 2 EI, and integration from 0 to A. This is U. So deflection at this point will be delta U upon delta P. This will give the deflection at this point. So this U, delta U upon delta P. So this will be two into Py into 1 into coefficient of P into dy plus partial derivative of this, basically U is equal to M square ds upon 2I. This is the formula. So delta U upon delta P will be 2M into delta M upon delta P into ds upon 2I. So this will be M into delta M upon delta P into ds. This is what exactly I am doing. So this will be partial derivative on this, derivative of this will be this one into coefficient of this, plus similarly this will become 2 into 2Pa, and coefficient of this P, coefficient of this Pa is equal to 2A into dx upon 2EI. So this will be 1 upon EI, I can take common. So this will be 2P into y square. Y square means y cube upon 3 plus this will be 4 Pa square, and this will be x. So one upon EI, this P into A cube I can take common. So this will be 8 into 2, 16 upon 3 plus 4. This will be PA cube upon EI into 28 upon 3. So 28 upon 3 PA cube upon EI means this one is the right option. Now which one of the following is the reaction of the cantilever at B? So in this case, this beam will provide some reaction here. So this will be like this. This beam will provide some reaction. Suppose this reaction is R, this is W per unit length, and the same reaction will be here for this simply supported beam. This is CD. If this beam will provide some reactions R, and the same reaction will be here, so this is R, and this length is also equal to, this is at the center, L by 2, L by 2. This length is also equal to L, means length, this length is also. So in this case, my net deflection will be equal to this deflections. This net deflection will be how much? This will be deflection because of this UDL. This is WL4 upon 80I minus due to probe, this will be upward. So it will be RL cube upon 3I. So this net deflection, this minus this deflection is equal to this deflection, and this deflection is equal to RL cube, this is simply supported beam, upon 48 EI. So L cube, this will be L here, EI and EI. So it will be WL upon 8 minus R by 3 is equal to this is R upon 48. So WL upon 8, this will be, if I take, this will be R upon 48 plus R by 3. So R by 48, if I take common, this will be 1 plus 16. So it will be 17 upon 48 R, and this R will become WL upon 8 into 48 upon 17. So this will be 16 upon 7, 17 WL. So this one is the right option. So this is a hinge. What is the reaction at the reaction on the pin C of the beam shown in the figure? So if you see, I can draw, this will be like this. This hinge will provide some reaction, and this is a cantilever. So the same reaction will be provided here. So this is L, and this is also equal to L. Means my net deflection here is equal to this deflection. So this deflection is equal to deflection due to this minus this. This is W. So this will be downward and this will be upward. So my net deflection at this point will be, this is W L4 upon 8EI minus due to this prop, it will be RL cube upon 3I, and this will be equal to, this net deflection is equal to this net deflection, then this is equal to RL cube upon 3I. So this is WL upon 8 is equal to this R upon 3, this is R upon 3 plus It will be 2 R upon 3 is equal to WL upon 8, and this reaction R will be WL upon 8 into 3 by 2. So this will be 13, 3 upon 16 WL. So this is the right option. A simply supported beam AB of span 4 meter is subjected to a terminal couples as shown in the figure. This is 4 kilonewton and 4 kilonewton. EI is kilonewton meter. So what is the magnitude of the center deflection? So there is a central deflection. I have to find. So for this, what I can do? I can use the conjugate beam method. So its moment will be like this. Both are, this is sagging, this is also sagging. So this is 4 kilonewton, this is 4 kilonewton, and this will be simply supported. So this will be 4 upon EI and 4 upon EI. So this is conjugate beam. My deflection at the center will be deflection at the center of the real beam is equal to moment of the center of the conjugate beam. So I will take the moment at this point. So moment will be, first I have to find the reaction. So reaction will be total, this is 4 into this is 4. So this is 4 into this length is also 4. This is the total 16 upon EI is the total load. So this will be half 8 upon EI and 8 upon EI. 4 into 4 the total load. So this reaction will be half of this. So it will be 8 upon EI. So the center deflection will be, I will take the moment at this point. The moment at this point will be 8 upon EI, this into length, this is L by 2 minus this will be 4 upon EI into L by 2 into half of this L by 4. Oh, this will be, basically this L is 4, so it will be 4. So 8 upon EI and this will be 4 by 2 means 2. So this will be 16 minus 8 upon EI. So 8 upon EI is the bending moment in the conjugative beam, means deflection at the real beam. So this one is the right answer. So what is the moment at A? Moment at A. This is I, this is I. So if you draw the free body diagram, it will be like this. So this member will provide some reaction at this point. Suppose this is R. and this will be like this, compressive force, and for this beam it will be like this. So whatever my net deflection at this point, the same will be, it will deflect. This deflection is equal to this deflection, and this deflection, this will be P, this is 2L, so this is 2L, so P into 2L cube upon 48 EI minus R into 2L cube upon 48 EI. Deflection because of this will be like this, and because of this direction it will be like this. So this minus this will be the net deflection, and this net deflection will be equal to this deflection, and it is R into 2L cube upon 48 EI. So this 48 EI, this will cancel. RL cube cancels. So this will be P minus R is equal to P. Sticks there. Oh, this is R basically. This is R. It is R. This is R actually. So this will be R. So P is equal to 2R means R is equal to P by 2. It means for this portion, this diagram will be like this. So this is P, and this R is equal to half of this P. So I can say my net load at this point is, I can treat it like this. So this minus this is the net load. This will be P by 2. Now moment at this point, if I want to know the moment, then half of this will be the reaction. So it will be P by 4, P by 4. The moment at this will be, this is P by 4 into this distance, and this distance is equal to L. This will be PL upon 4. So this PL upon 4 is the right option. If the hinged end of a proud cantilever of a span L settles by an amount delta, this is my proud cantilever. Then the rotation of the hinged. If the hinged end of a proud cantilever span L settled by the amount delta, then the rotation of the hinged end will be like this. Suppose this is a W load. Because of this, there is a deflection, and this is delta. This delta is equal to what? W L square L cube upon 3I. So this is the formula. This delta is equal to W L cube upon 3I. Suppose this is the load. Now the rotation at this rotation, this is the rotation, theta is equal to, what is the formula? WL square upon 2I. This I have to know. So this divided by this, I will get WL upon 3 into 2 upon W is equal to delta upon theta. This is the slope rotation which I have to know. So this theta, this is 2L by 3 is equal to delta upon theta. So theta will be 3 delta upon 2L. Means this one is the right option. What is the deflection at the hinge for the beam shown below? In this case, if I draw the free body diagram, so it will be like this. So this is P. This hinge will provide some reaction, and the same reaction will be here. So whatever will be the deflection at this, the same deflection will be here. My net deflection at this point will be equal to, this is a cantilever, you can say proper cantilever. So this will be P into this distance L by 2 3 upon 3I. This is the deflection because of this load, and due to this prop reaction it will be minus R into this distance upon 3I, and this net deflection, the net deflection will be something, so it will be like this and this, and this net deflection is equal to this deflection. This is R and this is L by 2 cube upon 3I. This 3I and 3I goes L by 2 cube, L by 2 cube and L by 2 cube. So this will be P minus R is equal to R. So is equal to P is equal to 2R, means R is equal to P by 2. So R is equal to P by 2, and deflection at this point is equal to how much? This deflection is equal to this net deflection. So deflection of this cantilever is RL cube upon T, which is equal to the net deflection at this. So deflection is equal to, this is RL cube, R into L by 2 cube upon 3I. This is the formula, and R is equal to what? P by 2. So this is P by 2 into L cube upon 8 into 1 upon 3I. So it will be PL cube upon 48 EI. PL cube upon 48 EI means this is the answer. The compatibility conditions in terms of strain in a two-dimensional problem are associated with what? Compatibility condition in terms of strain in a two-dimensional. Compatibility conditions, compatibility always, it will be deformations, not stresses or forces. So this is a deformation. Suppose this is a proper cantilever. So my net deflection due to this is equal to deflection due to this. So this is net deflection is 0. So this is nothing but a compatibility condition. So it deals with deformations. This is the right answer. A cantilever carries a UDL out. Total load is W. Means this is a UDL and total load is, this total load is W. It means the intensity will be W upon L. So this small w is equal to W upon L. This is the intensity. And a concentrated upward load W at the free end. Concentrated upward load. Upward load means you can take it like this or like this. So this is upward load equal to this same W. The net vertical deflection at the free end. The deflection. So this I can treat it like this. This is W upon L is the intensity. This will deflect like this, and this upward W my beam will cantilever will deflect like this. So the net deflection at this will be this minus this deflection minus this. If this is delta 1, this is delta 2, my net deflection will be delta 1 minus delta 2. And what is delta 1? Delta 1 will be, formula is WL 4 upon 8 EI. This is the formula for deflection, minus this is W L cube upon 3I, and this W is W upon L into L4 upon 8I minus WL cube upon 3I. So this will become WL cube upon 8I. So this WL cube upon 8I, I can take common. It will be 1 upon 8 minus 1 upon 3. Means this will be 24. So it will be minus 5 upon 24. WL cube upon 24 means my deflection is in the upward directions. The net deflection is upward directions. This is 5 upon 24 means this one 5 upon 24. Yes, since this is minus, minus means this deflection is more, so that the upward deflection is more. So minus means my deflection is in the upward direction. So this one is the right option. If a cantilever beam of span L and flexure rigidity EI carries a moment like this, carries a moment M at the free end, then the deflection at that end. So deflection at this will be equal to, if a cantilever beam of span L and flexurity carries a moment M at the free end, the deflection at the end will be, if I draw the bending moment for this, it will be like this. So this is hogging, so it will be like this. This is hogging, so this is my, and this M will be constant throughout. So it will be M upon EI. M upon EI is the conjugate beam, and the reaction will be like this. And this fixed end will become free, and this free, this end will become fixed in the conjugate beam. So my deflection at this end, my deflection at this end means my bending moment at this end in the conjugate beams. So I have to take the moment at this. So it will be M upon EI into this length is the area, and it will act half of this space. So it will be L by 2 So this will be ml square upon 2ei. ml square upon 2i is the bending moment in the conjugate beam, is deflection at the free end in a real beam. So this one is the right option. For the beam system shown as shown, if the deflection at C is 0, my deflection at this C is 0, then the ratio of P upon Q is equal to how much? So my net deflection at this point C is 0. So this will be like this. This is P and this is L and this is L. So it is 2L total. And this is a propriection. This is Q. So this will deflect like this, and because of this Q, it will deflect like this. Show that my net deflection at this point is 0. It means my deflection because of this P at this point is equal to deflection because of this Q which is acting at this. Now deflection this is equal to, this will be P into, this is 2L cube upon 3I. This is the formula. This deflection is equal to P into 2L cube upon 3I, and this will be equal to this deflection, and this deflection is equal to my this deflection at this point plus my slope here into this distance. So this will be Q into this length plus slope at this point into this length. So EI and EI will go. L cube will also go. So it will be 8 P upon 3. This is equal to Q upon 3 plus Q upon 2. So this will be 5 by 6 Q is equal to 8 by 3 P, and P upon Q, this upon Q will be 5 upon 6 into 3 upon 8, and this will be 5 upon 16. P upon Q is equal to 5 upon 16. Means this one is the right option. For the beam system as shown, if the slope at M, is 0, then the ratio of T upon S is how much? So I can treat it separately. So it will be like this. This is M, this is T. So this will deflect like this, and because of this S, my cantilever will deflect like this. What he says, that the slope at this M is 0. Slope, my net slope is 0. It means if I draw a tangent, then this, if this is the theta, so in this case also if I draw, it will be theta. Means this rotation, clockwise rotation is equal to this anti-clockwise rotation, so that my net deflection at this point is 0. It means slope because of this P is equal to slope, this slope. This slope is, this is theta 1, this is theta 2, and this slope is equal to how much? This is P into, this is 2L square upon 2EI. This is the formula, WL square upon 2EI. Slope because of this will be this. And in this case, from this point onward, it will be a straight line. So whatever will be the slope at this point, this slope will be continue. So it will be parabolic from here to here, but from Q onwards, it will be a straight line. So my slope at this point is equal to slope at this point, and slope at this point is equal to how much? This is Q L square upon 2EI. The same slope will be here. So it will be Q L square upon 2EI. This L square will also go. So it will be 4P. This is 4P is equal to Q. So P upon Q will be 1 by 4. Sorry. This is T. Basically, this is T. And this is S. So this will be S. So Q will be S and P will be T. So T upon S is equal to 1 upon 4. So this is the right answer. For the beam, the reaction of the beam at C. This is a hinge. So as I explained earlier, this hinge will provide some reaction and the same reaction will be here. So this will be a propped cantilever and this will be a free cantilever. So my net deflection at this point will be this one. This UDL will deflect like this and this R will deflect like this. So my net deflection at this point is equal to, suppose this is the net deflection, so the same deflection will be at this point. So net deflection, this will be W. This length is, I think, same. This length is same. So this will be W L4 upon 8EI minus, because of R, it will be R L cube upon 3I. So this will be the net deflection, and this net deflection is equal to this deflection, which will be, this is L, this is L. So RL cube upon 3I. So L cube EI and this. So it will be WL upon 8 is equal to 2 times of R upon 3. So this reaction is equal to WL upon 8 into 3 by 2, and W is what? This is 10 kilonewton per meter into the length is this one, and this is 4 meter upon 8 into 3 by 2. So this will be 15 by 2. 15 by 2 means 7.5. This one is the right option. A simply supported beam of span L is subjected to a concentrated load W at the midspan and also to a UDL load equivalent to W. This is UDL, and this total intensity of this W into L is equal to this W. Means this intensity is equal to W upon L per unit run. This is capital W upon L is the intensity here. It has a flexure rigidity of EI. What is the total deflection at its midspan? So my deflection will be, this is equal to my deflection due to this UDL, which is W upon L, is the intensity, plus my deflection due to this W. So this is a principle of superposition. So these will be deflections. So my net deflection because of this concentrated load plus this UDL is equal to this plus this is equal to my total deflection. And this deflection is equal to how much? Formula is W 5 upon 384 WL4 upon EI. This is the formula, plus this is equal to WL cube upon 48 EI. This in case, and in this case this is 5 upon 384 and my small w is equal to W capital W upon L into L4 upon EI plus WL cube upon 48 EI. So if I take WL cube upon 384 EI common, so this will be 5 plus this will be 8, so it will be 13, this will become 13 over 384 WL cube upon EI, means this one is the right answer. Mid-span deflection for the beam load shown below can be obtained by, so this is a simply supported beam, this end is roller, this is hinged, this load is there. So my mid-span deflection, this deflection can be obtained by area moment method, yes. Strain energy method, yes. Conjugate beam method, yes. Generalized 3 moment equations. Can we apply the 3 moment equation in this? Yes. I can apply the 3 moment equation also like this. So suppose this deflection is delta. So I can assume it like this. Suppose if I apply this P here, so this is equal to like this. So this is a downward. So if say I can say this is A, this is B, this is C. Oh, this is C and this is B. So my this I can say this my P is reaction at B. This reaction at B is equal to P and this is downward. So this is downward. So and there is a deflection of delta. So I can consider both this span, this AB, this is AB and BC, and I can apply a 3 moment equation treating this are 2 different span and taking this delta. So we can say my this support is there is a settlement of delta. So I can find the moment at this point, and this moment is 0, MA is equal to 0, this moment is 0. So I can use the 3 moment equations and find this delta. So 3 moment equation can also be applied. It means all are correct options. So 1, 2, 3 and 4, this is the right answer. Total deflection of a structure when subjected to simultaneously to different set of loading is equal to the sum of the deflection under each such set of load as if it acting separately on the structure. Which one of the following justifies this statement? As I have discussed in the previous example, this is the UDL and this is W. So I can treat it separately for UDL and this concentrated load. So this is nothing but a principle of superpositions, and I can do it. So total deflection is equal to my deflection because of this and my deflection because of this. So this is the total deflection. This is equal to this plus this. Which of the following justify the statement? Elastic limit is not exceeded. Elastic limit including buckling is not exceeded. Limit state is not exceeded. Proportional limit without buckling is not exceeded. So this is basically principle of superpositions, and principle of superpositions is basically dependent on the Hooke laws. So this is on the basis of Hooke laws, and what Hooke law says that stress and strain is proportional to each other within the proportional limit. So this is basically Hooke law. So this proportional limit without buckling is the exceeded, not exceeded. This is the right option. So this is a simply supported beam, equivalent spring constant for the set shown in the below figure when EI is unit. So EI is equal to 1 throughout. So there is a spring and its stiffness is 48 unit. Another simply supported beam. So if I treat it separately, then if I draw the free body diagram, it will be like this. This spring will provide some reaction. Suppose some load is acting, P. So this is P, and there is some compression. So this will be compressive R, and in this beam there will be force R. So this is 0.5 meter. This is 1 meter. This is 1 and 1. So in this case, my net compression of these springs, is equal to my this deflection minus this deflections. So if this is this deflection, so my net deflection at this point will be, this will be P minus R into this length will be 1 and 1, 2 upon 48 EI. So my net deflection, this deflection minus this deflection, this will be R into this length is 1 cube upon 48 EI. My net deflection, this deflection minus this deflection is equal to my net compression of the springs, and compression of the spring is, the load in this case is R and stiffness is 48. So it means load upon this K will be the deflection, and this will be R upon 48. So this will be R upon 48. R upon 48 is this one, and this EI is basically 1. It means this is 1. So it will be 48, 48, 48. So this will be P minus R into 8 minus R is equal to R. So this will be 8P minus 8R is equal to 2R. and this 8p is equal to 10r, means r is equal to 8 by 10 means 4 by 5 p. So r is equal to 4 by 5 p. So this reaction r is equal to 4 by 5 p. So this r is equal to this one, and the equivalent spring constant so this is p and this r is 4 by 5 p. This r is equal to 4 by 5 p. It means my net deflection at this will be, as I know, p minus r cube upon p minus r into 2 cube upon 48 EI. This is the deflection here. So this p minus r means p minus 4 by 5 p into 8 upon 48 EI is equal to 1. So it will be 1 upon 6, and this is p by 5. So this will be p by 5 into 1 by 6. So this will be p upon 30. So p upon 30 will be the deflection delta at this point, and this load p upon this delta will be 30, and this load upon delta is equal to nothing but the equivalent stiffness. This is the equivalent stiffness of this set. So this will be 30 unit. A hinged board is in a real beam becomes an internal hinge in a conjugate beams, changes to a free spot in a conjugate beams, changes to a fixed spot in a conjugate, remains hinged as a hinged spot in a conjugate. So it will remain hinged. If this is like this, in a conjugate beam also this will be hinged. So hinged end will remain hinged. This is the right answer. For the structures shown in the figure, all of I, EI, L are respective unit value. Means this L is 1, this EI is 1. The equivalent stiffness constant for the structure is equal to how much? This is the same which we have discussed so far. So this is a cantilever. Suppose some load P is acting. So this spring will provide some reaction here. This is downward, this will be upward, and the same downward reaction will be here. So my net deflection at this point minus this deflection, my net deflection in this point will be P minus R into this length is 1 upon 3 EI. EI is also 1. This deflection minus this deflection, this will be R This length is also 1 upon 3 EI. EI is 1. This minus this will be equal to the compression of the springs, and this compression of the spring will be R upon this stiffness, and this is 3. So it will be R upon 3. So this will be P minus R is equal to R. So P is equal to R plus R plus R is equal to 3R, means R is equal to P by 3. R is equal to P by 3. So it means if this R is P by 3, then this load is P. So there is a downward load of P and this is upward load of P by 3. So my net deflection at this point is equal to how much? My net deflection, this is P minus R, this minus this. So this will be P minus R is equal to P by 3. This into 1 cube upon 3 EI. So it will be 2P by 3 cube upon 3 EI. EI is 1. So it will be 2P upon 9. So 2P upon 9 means P upon 9 by 2 is equal to P upon 4.5. And this is the deflection at this point, delta. So this load P upon this deflection delta is equal to nothing but the equivalent stiffness. This will be 4.5. Two simply supported beams are made of the same material and are of the same cross section. Both beams carry UDL of equal intensity. One beam is 2 meter long and the other is 4 meter long. The 2 meter long beam shows a center deflection of 1 mm. What is the center deflection of 4 meter long? There are two beams. One is 2 meter. One beam of 2 meter long and other is 4 meter. Both beams carry uniform distributed load of equal intensity. So this is W, this is W. This one is for 2 meter, other is the 2 meter beam shows a center deflection of 1 mm. Means this deflection is, this delta is 1 mm. So what will be the delta here? What will be the center deflection in this? It means both are simply supported. So for this, my deflection is, this deflection will be equal to 5 upon 384 W into length WL4 upon EI. This is the formula, and this deflection is equal to 1 mm, and deflection because of this will be 5 upon 384 W into 4 raised to the power 4 upon EI, and this is the deflection. Suppose this deflection is delta, which I have to find. So this divided by this divided by this, what I will get? This will cancel, EI will cancel, WW will cancel. So this will be 2 upon 4 raised to the power 4 is equal to 1 upon delta. These are in meter and mm, so it will not make a difference. This will be 1 by 2 raised to the power 4 means 1 upon 16 is equal to 1 upon delta. So delta is equal to 60 unit. So this is 16 mm is the right option. If the deflection at the free end of a uniformly loaded cantilever beam is 15 mm, this deflection is 15 mm, and the slope at the deflection curve at the free end is 0.2 radian. My deflection is this and slope is this, theta is 0.02. Then the length of the beam is how much? What is the formula for deflection? This is WL cube. Then due to UDL it will be WL4 upon 8EI. This is the formula for deflection, WL cube, WL4 upon 8EI. In case of UDL, this deflection is 15 mm, and this rotation theta slope. What is the formula for slope? It is WL cube upon 6EI in case of cantilever. This is equal to 0.02. If I divide this by this is equal to this by this, so it will be W and W will cancel, EI, this L cube, and this will be L. So it will be L upon 8, and this will be 6 upon 1 is equal to 15 upon 0.02. So this is 3 by 4. So L is equal to 15 into 4 by 3 into 0.02. So this will be 20 upon 0.02 means 2 upon 100. So this will be 1000 mm. Since this is in mm, this is in mm, so 1000 mm is 1 meter. This is the right answer. Assessment and reasoning. Macaulay's method to determine the slope and deflection at a point in a beam is stable for beams subjected to concentrated load and can be extended to UDL. Yes. Macaulay's method is based upon the modification of the moment area method. Wrong. Moment area method is different and Macaulay's method is basically a double integration method. So both are different. This is applicable to simply supported carrying a single UDL considered, but by superposition this method can be extended to any of the kind. Basically this is wrong. Both are different. This is double integration, this is moment area. So A is true and B is false. So this A is true and B is R is false. This is the right option. In a cantilever span of L subjected to, this is a cantilever span and it is subjected to a cantilever load of W acting at a distance of L by 3 from the free end. Oh, this is so this is basically acting at this point W, which is L by 3 from the free end, means this is 2L by 3. So this is the free end. The deflection under the load will be how much? Deflection under this load. So at this deflection under this load. So this deflection under this load will be, I will forget this part, I will treat this as a cantilever and load is applied at this point. So this deflection will be W into, I will treat this L. I will forget this, it will be W into 2L by 3 raised to the power 3 upon 3I. So it will be W into 8 L cube upon 27 into 3 EI. It will be 8 upon 81 WL cube upon EI. So this will be the right option. A simply supported beam of uniform flexure rigidity is loaded as shown in the figure. The rotation at the end A. So in this case, I can use my conjugate beam method. So the bending moment of this will be like this. The same reaction, this symmetrical, so it will be P and this will be P. So my bending moment will be like this, PL by 3. This is PL by 3. Since reaction will be P and P here, so this is my bending moment and this will be sagging. So if I divide it by EI, then it will become my conjugate beam, and this hinge will remain hinge and this roller will remain roller. Now the rotation at this point theta, slope means rotation means slope in the real beam is equal to shear force at this means reaction. So reaction will be equal to shear force here and that will be equal to the slope in the real beam. Now this is symmetrical, so my total load will be, this is L by 3, this is L by 3 and this is also L by 3. So my total load, this total load is equal to how much? This will be equal to area of this. So area of this is 1 by 2 into PL upon 3I. This is PL upon 3I, this side into this side. This is L by 3. So L by 3 is this into this. This is PL upon 3I. This is L by 3 into 1 by 2. And the same, this will be same. So this I will multiply it by 2. This load plus load of this central portion. So this is PL upon 3I into L by 3. So it will be PL square upon, this is 9 EI. If I take this common, this will be 1 plus this is also equal to 1. So it will be 2 upon 9 PL square upon EI. And this is the total load. So half of this total load will be the reaction at this point. So half of this will be PL square. I will divide by 2. So this will be PL square upon 9 EI. So this reaction at this is PL square upon 9 EI. And this is also PL square upon 9 EI. And this reaction at this point, basically this will be the shear force. This will be the shear force PL square upon 9 EI, like this. So this PL square upon 9 EI, the reaction at this point is the shear force at this point is equal to the slope of the real beam, means rotation at this. So this PL square upon 9 EI. This one is the right answer. A rigid cantilever frame of ABC is fixed at this point and carries a couple mu at the free end A shown in the figure, neglecting axial deformation and assuming the flexure rigidity EI to be constant throughout the frame. The vertical deflection at this point is equal to how much? I can treat it like this. This is mu. So you can, this is my couple of mu moment. This is A, B and C. This height is H, this is L. Now vertical deflection at this point, what I will do? I will put a imaginary load Q. Suppose Q is the imaginary load and apply the Castiglione theorem. My strain energy is equal to m square dx upon 2I. This is the formula. This is the formula for strain energy, and delta U upon delta Q will give the deflection. I will put the value of Q is equal to 0 in this. So now my Q is U is equal to, for this portion it will be, if I take this is X, so this will be both having the same direction. So both having the same direction. So it will be Q into X plus mu, this is m square into dx upon 2I. This I will integrate from 0 to L, plus for this portion it will be Q into L plus mu, QL plus mu, QL plus mu, this is the moment, this square into dy upon 2EI and integration from 0 to H. Now as I know, delta U upon delta Q will be derivative of this will be 2 into Qx plus mu raised to the power 1 into coefficient of this is x dx upon 2I plus this will be 0 to H 2 QL plus mu raised to the power 1 into coefficient of Q is equal to L upon 2I into dy, and I will put the value of Q is equal to 0. Since Q is an imaginary load, so I will put the value of Q is equal to 0. So it will be 0 to L 1 upon EI, and this will be mu into x dx, and this one will be, I will put the value of Q is equal to 0. So this will be mu upon EI integration from 0 to H, and this will become L. So this is L here, so means mu L and dy. So this mu upon EI we can take common, so this mu upon EI I can take common. So this will be x square by 2 means L square by 2 plus this is L into this will be y means H. So I can take mu L common here. So it will be mu L upon EI, and it will be L by 2 plus H, means ML upon EI into H plus L by 2. So mu L upon EI H plus L by 2. So this is the same. It means this one is the right answer. Match least one actual beam and conjugate beam on the basis of analogy. And select the correct answer using the codes given below. Slope of the real beam is equal to shear of the conjugate beam, shear force of the conjugate beam. The deflection of the real beam is equal to moment of the conjugate beams. So B3 and C1, B3 and C1. And curvature is, what is curvature? Basically M upon R EI is equal to E upon R. So this 1 upon R is equal to M upon EI. So 1 upon R means curvature, and curvature is equal to what? This M upon EI, suppose this is the central load, so its bending moment will be like this. It will be W up means M. So when we divide M by EI, M divided by EI will give the loading. So this will give the load of the conjugate beams. So 1 upon R is equal to M upon EI means load of the conjugate beam. So this is CA2. So A2, A2, B3 and C1. A2, B3 and C1. This is the right option. A simply supported beam A carries a point load at its mid span. Another identical beam B, this is my beam A. Another identical beam B carries the same magnitude of load but is uniformly distributed. So my this load is also W, but it is uniformly distributed. Suppose this is L, this is also L. The ratio of the maximum deflection of the beam A, this will deflect like this, maximum deflection will be there. So this will be delta A and this is delta B, beam B. The ratio of the maximum deflection of beam A and B means delta A upon delta B. So maximum deflection in this case it will be WL cube upon 48 EI. This is for delta A, and delta B deflection in this case, this will be 5 upon 384 WL 4 upon EI. And I can say this WL 4 upon, this is L3 upon L1, and this WL is equal to basically W. So I can say this is WL, this W small del, this intensity is basically W upon L. Intensity will be W upon L. So we can say W upon L is the intensity into L4. So it will be W L3. If I divide both, then this WL cube will go So it will be EI will go 1 upon 48 into this will be 384 upon 5 is equal to theta A delta A upon delta B, means the ratio of the maximum deflection of this upon this, and this will be 8 upon 5. So 8 upon 5 means this one is the right answer. The maximum deflection of simply supported beam occurs at 0 bending moment location, shear force location, slope location, shear force location, and also 0 bending moment locations. Suppose this is my simply supported beam carrying a UDL, it will deflect like this. So my slope at this point, this is horizontal, so my theta at this point dy upon dx, which is the slope is 0 here. So where the slope is 0, my deflection will be maximum. So when slope is 0, my deflection will be maximum. So it will be slope location. With the slope location, it will give the maximum deflections. So this is the right answer. Which one of the following is determined at a point of a given beam by moment area method? It is moment area method is used to find the slope and deflection, not for bending moment and shear force. So this is 3 and 4. 3 and 4. This one is the right answer. A simply supported beam of span L is subjected to a concentrated load W at mid span. The strain energy due to bending in the beam, strain energy is equal to m square ds upon 2ei. This is the formula for strain energy. So if this is W, reaction will be W by 2. So strain energy U is will equal. So if I take x, this will be W by 2 into x. So m square into dx upon 2ei, and this will be 0 to L by 2, and this will be same. So I will multiply it by this by 2. This from this is equal to this. So this will be 2. This 2 and 2 will cancel. So it will be W square upon 4 into x square into dx, means x cube upon 3. 0 to L by 2. So it will be W square upon 12, and this will be L by 2 cube minus 0. So this will be W square upon 12 into L cube, this L cube upon 8. So this will be W square L cube upon 96, and EI is also there, EI. So W square L cube upon 96 EI, W square L cube upon 96 EI. This one is the right option. Consider the loaded beam shown in the given figure. So this is simply supported beam overhang at the both the ends. Assertions the deflection at the free end C is A times the slope at A. So it will deflect like this. So my deflection at this point, suppose this is delta C, is equal to slope at the free end. My this slope theta is equal to this theta. So this theta into this distance will give the deflection at this. Yes. So deflection at the free end will be equal to the A times this distance is A times this theta will give the deflection at this. Yes. Reason is The elastic curve for the overhang portion AC or this BD is a straight line tangential to the elastic curve at A and B. Yes, if you draw a tangent, so this will be like this. If you draw a tangent, it will be that. So from this portion onwards, it will be a, so my tangent means straight line. Slope at this point is equal to slope at this point, and this will be this into this. So both are true, and this is the correct explanation of this one. So this one is the right option. Consider the following statement: a cantilever beam of L is loaded with a UDL of W on the span, uniform distributed load of W. The beam is propped at the free end. This is propped at the free end, having its level same as that of the fixed end, means deflection at this point is 0. So prop reaction is how much? So my net deflection because of this UDL is like this, and due to prop it will be like this. So my net, this deflection is equal to this deflection, and this deflection is equal to W L4 upon 8EI is equal to, due to prop it will be RL cube upon 3I. So R will be WL by, this will be 3 by 8 WL. So my prop reaction is equal to 3 by 8 WL. So this is right. The bending moment at the prop is WL square. Wrong. My bending moment is 0. The prop reaction is WL by 2. This is also wrong. Shear force is 0 at X is equal to 3 by 2. Yes. If you see, this is like this. This is 3 by 8 WL. So my total load is W. So shear force at this X, if I draw the shear force at this X, it will be upward, means minus 3 WL upon 8, and this is downward, so this will be W into X. My shear force will be 0. It means 3 by 8 WL is equal to minus WX, minus minus cancel, WW cancel. So X is equal to 3 by 8 WL. It means at X, when X is equal to 3 by 8 WL, the 3 by 8 of L, my shear force will be 0. So this statement is also true. So 2 and 4 are true, means this one. So this is the right option. A unique relation between bending moment M and intensity of load W acting continuously on a beam of span L at a distance X along the X-axis flexure rigidity of the beam is a unique relation between bending moment. This is a beam. Suppose, so at X distance, the intensity is W. So the unique relation is which one? As we know, EI into D second derivative y with respect to x square will give the minus m. It's dy upon dx. This will give the slope, and this will give the deflection. Its third derivative will give the shear force, and its fourth derivative will give the rate of loading W. So this EI into fourth derivative of y with respect to x is the W. And what is this? I can say EI into d square upon dx square of this is equal to W. I can also say. So, second derivative of this, second derivative of y with respect to x, it will give fourth derivative. And what is this? This is equal to m upon EI. This will be equal to m upon EI. So, I can say EI into so this will become m upon EI. This will become m upon EI is equal to W. This EI will cancel. So, this will be second derivative of m with respect to x is equal to W. Second derivative of moment with respect to x is equal to W. And this is what exactly this relation is here. So, this B is the right option. A straight cantilever of uniform cross sections carries a total load. This is the UDL. Total load is W. Means this intensity is W upon L. If the free end of the cantilever is now propped up to the level of the fixed end, then the vertical force required at the prop will, this R will be equal to, as we know, deflection because of this will be W L4 upon 8 EI. This is the deflection is equal to deflection because of this. This will deflect like this and prop will deflect like this. So, this deflection is equal to this one. So, this will be R L cube upon 3I. This is L cube. So, R will be 3 by 8 WL. And this is, yes, this WL is equal to W. So, this will be 3 by 8 W. This is the right option. So, this is the end of the lecture. I hope you enjoyed the lecture. So, thank you very much and good night.